Good morning, everyone. Now, the session will handled by Nagendra Nagaraju garu. Before going to starting the session, I want to introduce Nagendra Nagaraja garu. Sir is the founder and CEO of QPI AI. It is hybrid classical quantum compute targeted to solve optimization problem and AI machine learning quantum modeling. Sir is the founder and director of SuperQ Technologies India Private Limited, and he is the founder and MD QPI Cloud. And Sir worked in various companies like in as a specialist, lead engineer, and senior engineer. Sir has 8 years experience in Qualcomm. Sir completed his PhD at Coventry University. I request Nagendra Nagaraju garu to handle the class.
Oh, thanks a lot. Good morning,
Thank you, sir.
everyone. Yeah, thanks a lot. Good morning, everyone, and thanks for your time in attending this lecture. Okay, hopefully we can gain something out of it. So I'll be sharing my screen.
S- sh- Hello, sir.
Yeah, can you see my screen?
Yes, sir. It is visible, sir.
Okay, so let me share the presentation. Okay, so yeah, so today's topic is quantum for AI and AI for quantum. And to briefly introduce why I choose this topic, these are two different fields, which is one is physics and other is completely about intelligence modeling. And what is happening now is these two are actually coming together. I mean, they are coming together and collapsing. They cannot be separable in future. In near future, what is happening with the AI is the models are becoming bigger and bigger, and we have a compute with this current compute is a GPU, and it cannot handle that complexity, and we may soon move to quantum compute. So, given that the importance of these two, or the combination of these two, is what will drive when we look into next generation, coming generation. This is a combination of a skill set or the technology that entire world will run. Okay, so and other thing is if you look at quantum, it is so complex that it's like a combination of many supercomputers, right? And it cannot be handled by a human. You can't have an operator for quantum computer. It has to be handled by AI. So that's the topic we have chosen. Quantum is helping AI because it can accelerate bigger and bigger model, and AI is helping quantum because it can control the quantum compute better than a human. Okay, so that's the topic for today. But I will cover a lot of fundamentals, and then we go to the applications, and I will explain different application how AI can help the quantum. Okay. So this today what we have is understanding of fundamentals of quantum computing, discriminate between quantum size technology and hype. There's a lot of hype in any technology, and we should be able to discriminate that. Identify potential use cases and impact of quantum, and I will also explain how AI plays a bigger role in this journey, and I'll explain you some tools what we use, and we also explain what we are doing in QPI. Okay, so at any time we will stop. This is a big lecture, almost like 1 hour, and if you have any question, please stop by and you can just ask the question there and then. Okay, so why quantum computer? Why do we require quantum computer? Okay, so we do require quantum computer because there are some problem which cannot be solved by classical computer. No matter how much compute power you have, it cannot be solved. Okay, and some of these problems are a very pillar of human progress. Say, for example, for pharma, right? If you had a quantum computer which is at a scale, the drug discovery for COVID would have been done in almost like 20 days. We took almost a year, right? As a humanity, it took almost a year. And then there is a finance and risk management which is very difficult to do because it's a big optimization problem. And then, as I told you, a machine learning or AI. And then you have chemical and molecular discovery. See, chemical and molecular discovery is a very huge field. Actually, this is a very important field because the very basis of everything is what we do in materials or in a semiconductor, or maybe in a lot of this transportation and all those things that requires a very basic disruption in chemicals. Okay, like for example batteries, right? It's a chemical, right? So it's a lithium ion is a chemical, and we need to come up with the better batteries, right? So there we have to describe better molecule, and that depends on quantum compute, because the number of combination we have, it cannot be solved in billions of years using classical compute. We require quantum compute there. And then the material science itself, say for example, if you want to construct a rocket which is very light and which can be reused, and which can result in a longer travel, you require better material, lighter material. Okay, so there again you require quantum compute, because whatever we have done until now in material science, there's no breakthrough. Okay, like for example, if you want to have a room temperature superconductor, there is absolutely no way that we can do it manually. Of course, there are a lot of research going on, and I believe that strongly that quantum is one which will help in building room temperature superconductor, quantum and AI. Okay, and then efficient AI processes, and then energy efficiency is another thing. For example, if you want to transmit something without any loss, right, and that's a photonic, and that's again is a quantum, right? If you have a single photon detector and you want to transmit your light, okay, securely, that's again is energy efficiency, and that can be done by quantum. And logistics, for example, in India, we are going to go across a lot of these smart cities, right? Smart cities, one of the requirement is that the traffic decongestion. Of course, you guys in Anandpur, and you would have been very near to Hyderabad and Bangalore. These are very congested cities. Okay, and especially other cities like Mumbai and Delhi. So in order to decongest that, you do require a better algorithms to route the traffic dynamically. Okay, so that's what will make the smart city. And one of the way you can we are working on with major customers is we came up with an algorithm to actually solve the vehicle routing problem. Okay, that's currently is applied for only big logistic companies where they can route the vehicles efficiently, but it can also be applied for traffic control and traffic decongestion of smart cities. Okay, and if you look at what can be done immediately, material science and efficient AI processes we can do immediately, and chemical molecular discovery and machine learning model discovery. This can be done right now. In the longer term, drug discovery and finance, this under security. Okay, so these are the things which are longer term, but they have very high business value proposition. And especially when we come to chemical discovery and machine learning model discovery, they have huge business value proposition, because today we are hiring hundreds of data scientists to actually solve this problem, coming up with AI models. In future, it can be done automated way. You can just convert the unstructured data into AI model within clicks of a button. Okay, so that's the power of quantum compute. So these are the big opportunities what we have in quantum compute. Okay, and I will introduce to some of the fundamentals of a quantum principle. Okay, in the phase one. So before this, before going to this, any questions on the application? Okay, so I'll move to the fundamentals now. So classical compute is all on the bits. Okay, and this works on 0 or 1. There's no intermediate state. Like you have a simple, physical implementation as a switch using CMOS or transistors, and V low is 0 and V high is 1, and you have a sequence of bits like this. Okay, and what happens with this is computation. There is a sequential computation limits. Okay, you can't compute longer sequences. Okay, like for example, it will become memory intensive. Okay, and reversible computation, it's an overhead. Okay, so there's a lot of overheads when we do the reversible computation. For example, if you want to do the prime factorization, right? So that is very cumbersome in this kind of computation. Okay, and then cloning. Okay, so these are the things that we relied on for almost like 100 years, maybe like 200 years, or until now. This is the thing. Boolean algebra is there for a long time. Okay, and on this gates, classical gates is there for a long time. Okay, and we have built a supercomputer using this principle, okay, and which is fastest right now. So this is a classical information processing which is based on bits. Now, limitation of classical compute, of course, complexity. We cannot handle the complexity here. Okay, so if you look at different kinds of complexity, it is NP hard, PP hard, and then there is a BPP and PH, BQP, BQP. Okay, so this complexity cannot be handled by classical compute because it is polynomial time. Okay, it's not like linear or logarithmic. It cannot be handled by quantum classical compute. So we do require something of a different computation model to handle the complexity. Okay, so then coming to other problem we are facing in the industry is Moore's law. Moore's law is almost getting uh, it is getting flattened, and what we have today is if you add more number of transistors, more number of, if you go deeper into the technology node, like for example, if you go from 7 nanometer to 3 nanometer, you're not going to increase number of transistors. Okay, we are not packing that many number of transistor in a unit area, and we are seeing that Moore's law is coming to end because of the physics, limitation of physics. We can't go deeper and deeper, and when we go deeper and deeper, it is not resulting in more transistors, okay, or more computation power. So that's another problem we have with Moore's law, and that is coming to end. And only way we can build a bigger and bigger compute is using actually quantum computer. Okay, and energy consideration. Look into all this, big server processor and all. They produce a lot of heat. They produce a lot of heat because not because of the computation, but because they have to move the bits across the memory. Okay, and they have to actually their computation is like a lot of movement inside the memory and within the memory, within DRAM and your storage. So that will result in a lot of loss of energy, okay, and production of heat. For example, if you want to try in a deep learning model, what we require, it emits more, more carbon dioxide than, the vehicles across some area. Okay, so if you look at city of Bangalore, right, or city of Hyderabad, and if you see how much emission is done by vehicles, the the emission that is done by data centers for deep learning, it will be almost equivalent to that. Okay, because it produces a lot of heat, right, and it requires a cooling, and cooling is not environment sensitive. So these are the things that will actually give rise to use of quantum compute, because this is like dead end. Okay, so you can't go beyond this, and your rate of return on investment is very low going beyond this. Okay, so coming to quantum compute. So what is different in quantum compute? Because the very computation unit of quantum compute is based on quantum bits or qubits, right? So here actually we use superposition principle, and a lot of these qubits can stay in multiple states. Like for example, it can stay intermediate between 0 and 1, and whenever we sample that, it will attain one of the states. And this is very important because this gives us to encode large number of state space compared to bits which is 0 or 1. Okay, so coming to fundamentals, right? Let's go to fundamentals. Like what are the important mathematical fundamentals to understand the basic processing of quantum compute? First is complex number. I think you guys, you people are very well versed with complex number. No need to explain this. Complex number is representation of any number using in a complex plane. So this is a complex plane. What I'm showing you now. Okay, and then linear algebra. So basically everything factorization and superposition principle works on linear algebra. Like for example, if there is a two states, this will be similar to this. Okay, so this is our probabilities, and this is how they can be superposed. Okay, and it's all based on linear algebra, and I hope there is no introduction required for this. And some of the direct notations you have to note is like on the vector. So this is how the vector. This is a vector representation. It is called. It is also known as ket. Okay, this symbol, and this is a complex number representation, and this is a dual of ket. Okay, vector dual of this, and then there is an inner product which is represented by the scalar and the vector, two vectors, okay, and there's a tensor product, and then you have complex conjugate and matrix operations. These are the basic things that you need to have to learn the quantum computer. Okay, basic operations in the quantum computer. Now coming to the complexity theory. Okay, what is easily computable and what is not easily computable? Okay, so there is some of these algorithms which are inherently complex. Okay, complex in the sense they are NP complete problems. Okay, and there are NP hard problems, and there is there are BQP problems, and there's a P. Okay, so these are different classes of problem. If you have a P space here, okay, so we can say there is a NP complete problem where box packing, and and then you have traveling salesman problem or map coloring, okay, and then the P space is like an end-to-end chess or an end-to-end Go. These are all P space, right? And there is a graph isomorphism where can you make sure that equivalent graph is generated? That's an NP hard problem. Okay, it's very very difficult because you have to actually travel through state space. Okay, then again factoring the discrete logarithm, right? If you have a log, discrete log, how do we factor them? Okay, that is a BQP, right? And then you have something like graph connectivity and testing if number is a prime, and then the matchmaking. Okay, so these are all P problem, and these are not a simple problem to solve. This is very very complex, right? Because one is it requires a lot of resources, and then it may not be possible to solve with quantum compute because the classical compute because of time. So for example, prime number factorization for some very large number, it says it can take few thousand years to do that, okay, using classical compute. And with quantum compute, it can be done in few seconds. So that's the difference. So classical to quantum, what we have is a notion of effectiveness, because computation itself is very effective in quantum compute, and they do not change. And then the efficiency, it requires lesser space, lesser moving of bits, okay, lesser energy, okay, and it can do it faster. So that's an efficiency. So why we move from classical to quantum is for these two reasons: effectiveness and efficiency, and we can make some things possible which is not possible today. And what is the motivation for classic quantum compute? Because nature is quantum, it is not classical, right? So if you look at what and all our forefathers, big scientists who have told about, why we require quantum compute, especially Max Planck, who is treated as a quantum guru. Okay, so it's clearly that you cannot talk to nature effectively using classical compute. Okay, so you have to have something of a language which nature talks. Nature always talks in quantum, right? So that's the reason we require quantum compute, because we want to get closer to nature, and we need to design few things which is for a well-being of humankind, because our entire humanity is dependent on nature, and if you want to talk to nature, you have to talk through quantum. Now, so quantum computation, how did it form, and where we are right now? Okay, so for example, this is Feynman's experiment actually was the first thing where we say that model of universal quantum systems on a classical simulation of quantum system on a classical computers. Okay, that was done by Feynman, and then in 1985 we have a model of universal quantum computer, and then what we have is, a potentially realizable quantum compute was done by Lloyd in 1993. And then we have this Shor's algorithm, which is beautiful algorithm for quantum application. And that was done by Shor in 1994. Okay, it is a polynomial time algorithm for prime factorization. That proves that in quantum, using Shor's algorithm, you can do the factorization on a quantum computer very efficiently. Okay, that's very important landmark for us. And then 2001, Chung has realized this Shor's algorithm using NMR. Okay, and 2020, August 20th, 2020, access to quantum computer over cloud, it was given by IBM. Okay, so everyone can use quantum, although it is called NISQ. It's a noisy intermediate state quantum, but still you can do a lot of things on the cloud. And now even Amazon has come up with Amazon Bracket, so where you are going to do all these things on the cloud. So quantum size, now there was a doubt on quantum computer until 2020. Okay, so people were saying, is it feasible? It is not feasible. Whether we can really realize quantum computer. Now it's not about whether quantum computer is feasible or not, but it's about like what will be different application that we can run today. Okay, it's real. And then some of the prerequisites I want to take about this is, of course, we need to know some of the quantum mechanics. Okay, so basically, you need to know what is the wave function, how exactly that leads to a quantum interference. Okay, quantum interference is very important experiment which was done in Max Planck Institute, which shows that uh, there was a big, argument or big differences in ideology over the, nature of, photons, especially, right? And some people told it's a particle, some people told it's a wave, and finally we came to know that this can be represented by quantum interference. Okay, both as a wave and a particle. Okay, it acts as both as wave and particle. Okay, so that is a very basic of quantum mechanics. So if you look at where we got into quantum mechanics, this is because of this photon theory. Okay, so the nature of the way the photon travels. Okay, and this is very important. If you are seeing my screen, and if you can see the waves, right? So this explains the quantum interference. Okay, so this is a very basis of quantum mechanics, how quantum computers behave, because when there is a quantum computation going on, you never know what the outcome is. It is in an intermediate state, it's in superposed state, okay? And it will always be interfering with each other, right? Like for example, on the right-hand side, if you look at the way two fishermen are doing, and there is an interference of waves. So similarly, quantum waves also, like the quantum theory also has this kind of interference. And superposition is absolutely very important, because if you look at shows this dead cat theory, right? So basically, whether cat is, if you put a cat in a box, if you want to know whether cat is alive or dead, you'll never know in quantum world, because it can be dead and alive at the same time. And once we sample that data, so you are going to either decide it is going to be dead or alive, and that will also be interfering with quantum computation. Once you sample it, computation stops there, right? So these are two important principles, which is a foundation for quantum computation. And then there's a quantum interference coming to, as I explained on the photons, right? So what happens is you have when you actually put these photons to the gun and you have a slit and allow them to travel, it will form a particular pattern which is more like a Gaussian. Okay, so when you actually see the actually pattern it is forming on the screen, that will be dependent on the quantum interference. And this is the equation. There will be constructive and destructive interference, and then you have pattern formed finally. Okay, so this is also very important in quantum world. Okay, so we need to understand superposition and then also interference. Now, how this actually is important in complexity, computation complexity. So you have how hard is to calculate interference pattern with classical compute. Let's say that these are the interference pattern we have, and we want to calculate depending on number of layers, right? So it is impossible to calculate in quantum computer because it is exponentially complex via time. Okay, as we increase this number of layers, okay, and to calculate this interference will become very, very complex. Okay, so how do we compute this interference? One is, you have a constructively interference lead to right answers. Okay, destructive interference lead to wrong answer. Okay, so if you want to do any computation, these two interference are very important in terms of quantum world. Okay, and there is a phase. There's a lot of things that will come into picture to arrive at this. One is a probability, and the other is a phase shift. Now, other property of quantum world is decoherence. Okay, so decoherence is like disturbance in the quantum world. If you have a perfect superposition, you get perfect answer. But then there is a measurement noise. So when we measure, we will never be able to sample the correct state in one go. So that's the reason you have to multiple time, you have to sample, you have to have error correction code, and only then you get a proper quantum computer. Okay. So decoherence is a noise that is affected because interference of quantum system with the environment. Okay, and that will actually give rise to errors in quantum computation. Okay, so most of the quantum computation today is dependent on how long the quantum state can be coherent. Okay, to give an example, like it can go from few microsecond to millisecond. Okay, if you look at the semiconductor based quantum computer, it has around 20 millisecond. Okay, and superconductor is around maybe a few microsecond, right? And there is this ion based thing that is at around a few seconds. Okay, but then you cannot scale all the quantum computer. We are betting on semiconductor because its coherence time plus number of qubits we can add is very large. Any questions here on the basics? Okay, so I'll go to phase two. Okay, stepping into real quantum computer. So we actually come across this classical and quantum bit, and quantum bit is represented by superposition of vectors. Okay, so that's the basics of qubit. And coming to the Bloch sphere, okay, so we need to know something called as Hilbert space, right? And what I'm representing on the right hand side is called Bloch sphere. Okay, quantum qubit is represented by this. Okay, it can occupy any state in the Bloch sphere, right? And then we have the superposition is a unit vector in a Hilbert space, and then it's a mixture of 0 and 1. The Hilbert space plays a very important role in quantum computation, and this Bloch sphere is represented using Hilbert space. Okay, and then qubits, right? So two qubits is like two level quantum systems. Okay, so you have one is you have different kinds of qubits. Okay, one is a path qubit, as I told, with interference lights, right? So when we talked about interference and the splitting of photons, that is called path qubit. And other is a spin qubit. Like typically in CMOS, in the semiconductor, if what chip we are building is based on spin qubit. Okay, it is based on electron spin. So you have a one spin of electron we can represent it by 0, other spin we can represent it by 1. So that is called spin qubit. Okay, and then we have a polarization qubit, which is based on purely the polarization logic on using light. Okay, and there's a charge qubit. You have a negative charge, and you have charge and charge surface. Charge is negative charge, and then charge is no charge. And then depending on that, we have two states, 0 and 1, and we can form a qubit. And today we are betting big on spin qubits because that is more scalable compared to all other qubits. And what happens when we bring more qubits, right? So when we bring more qubits and composite system of qubits, right? So it has to be represented by equation of superposition. Okay, more qubits you add, more factors you have in the equation. Okay, and this is how we scale the qubit. And the big problem in scaling this kind of qubit is noise. Okay, so there is no noise represented in this equation. You can add noise here, and that will disturb your calculation. And less of the noise, better the more accurate the calculation is on this qubits, composite qubits. And then this is another important property here. Okay, entanglement. So entanglement is very important because I can design as many qubits as possible, but if they're not entangled, the power of their computation power is very less. Okay, so what is entanglement? Entanglement is like two qubits. You can, if you know one qubits, you know other qubit. Okay, so it's like one qubit is 0, other qubit is 1. You don't need to measure other qubits. Okay, so you will naturally know that if this qubit is 1, other qubit is 0. Okay, that is called entanglement. Okay, physical property are found to be correlated, like position, momentum, spin, polarization. Correlation cannot be explained classically. This is a quantum property. There is nothing equivalent to this in classical world. Say, for example, you have one qubit here on Earth and other qubit on Moon, right? Still, they are entangled. right? So that is one of the unique property of quantum world. So quantum entanglement can be explained using the polarization of photons. Okay, so if you have a beam and the crystal, and we split this, and then you have different photons arriving at different state. You look A and B, right? So A and B are already always entangled. It can be one is in our solar system and other is in different solar systems. Still, they are entangled. They behave exactly opposite to each other, or the way they are tied to each other. Okay, distance doesn't matter. And here the problem happens is the theory of light, right? There was a big confusion between, I think, Bohr and Einstein, saying that if these two are far apart and you can measure them, then this is faster than light, right? So but still, I think it was proved that the later Bohr was correct and Einstein was wrong on this. And still there is a debate going on this. So computation with qubit, how do we compute? We use a Bloch sphere and Hilbert space, and we use a superposition principle, and we use different, the vectors, and then we finally compute the composite qubit. Okay, so all these things can happen in a rotation in a Bloch sphere. It is called unitary transformation. Okay, so that's how we compute the qubit. Okay, finally, when we observe, this is a logic we apply for observation. So now coming to the basic principle of all this quantum computation is based on quantum gates. Okay, quantum computation, the gates are different from actually the classical one. And if you want to have if you want to build a quantum computer, you need to build a quantum circuit first. Understand a quantum circuit. So all quantum computers are built on quantum circuits. So basically, what happens in the quantum circuit is like you have different gates for unitary transformation, and we going to combine them. Say, for example, these ones are qubits, and these are gates. Okay, so if you want to do some computation on this, you have to put these gates, and finally you obtain the answer over the time. Okay, so what happens to these qubits over the time with this quantum computer? Okay, and we have a different types of gates in quantum world. Okay, so if you look at if you look at a logical gate for single qubit gate system, so this is how it is. It behaves actually. It can be X gate, Y gate, Z gate, and it is represented by rotation in the Bloch sphere. Okay, so and everything on the single qubit can be calculated on a Bloch sphere, and when we combine them as a composite qubit, so you have an equation to combine them, and we can obtain the composite qubit. So there are other gates called Pauli gates, right? So these are all like it looks like Hadamard. Maybe you can't say it Hadamard. Pauli gate, Pauli X, Pauli Y, and it is a particular transformation that a bit undergoes. Say, for example, X is this matrix, okay, and when we actually put 0 or 1, this will interact with this matrix and answer. And similarly for Pauli Y and Pauli Z. Okay, any questions? Okay, so other gates or logical gates, it's a two qubit gates. So far we talked about single qubit gates. Now we talk about two qubit gates, and this is formed using like logical gates like control NOT and C phase or CZ gate. CZ gate is very complex gate. Okay, and this can be represented logically by a Bloch sphere or a polyhedron. Okay, polyhedron representation of these gates are very important because we will come to know a lot of distribution via this. And there are third part of gates are called Clifford gates. So in this we have Hadamard gates, phase gate, and CNOT gates. Okay. So this is for bigger number of qubits. You can combine bigger number of qubits on these gates and obtain the logical answers. So now we know about quantum representation of bits, and then we also know about bits. Okay, so how do we calculate? How do we measure all these bits, right? So basically, there are many bases of the vector space with which it can be measured. It can be on the x basis, and then we measure on z basis, and with probability we arrive at what is the final qubit state. Okay, there is no what do you say representation 0 and 1. It's all in the probabilities on the on this basis measurement on different bases. So now coming to how universal quantum compute is built. It is built on universal quantum gates. Okay. So there are different kinds of quantum compute. One is you have quantum annular and universal quantum gate quantum computer. So universal quantum computer is based on the principle of universal quantum gates. Okay. And then quantum annular is based on quantum word of simulated annealing. Okay. Any questions? Okay, so now coming to algorithms and processors, we have this gates covered. Okay, so there's a quantum full adder. If you want to have a quantum half adder and full adder, it can be done using quantum gates. Okay, different quantum gates we talked about. Okay, single qubit quantum gates, Pauli's gate, and then we have two qubits quantum gates. So can use combination of that to come up with half adder and full adder. So most of the algorithms can be derived using these gates. Okay, and then you one more thing, one big algorithm is called quantum teleportation. Okay, sending quantum information. So basically, you can actually create an entanglement first, and then you have to measure the Bell state. Bell state is the state of this quantum system. Okay, measure the Bell states, and then you have to convert them back to classical bits, and you can transport this information very efficiently compared to the classical communication. But still, this is a very far off thing. We have not really obtained any breakthrough here until now. And then there is another algorithm of super dense coding. This is very important because you can do a lot of this coding very densely using quantum computer compared to the classical one using the simple gates. And then quantum Fourier transform. So you have learned classical Fourier transform, and you can using the class this quantum gates you can construct Fourier transform. Okay, and it all similar to our classical Fourier transform, but it will be very fast, much faster than actually the classical Fourier transform because of Shor's algorithm. This is very important states GSZ state because this gives you a very compact representation of very large number of qubits. Like for example, if I want to represent 3 qubit system, it can be represented by GSZ states. Okay, and correction of noise is very easy with these states. Now coming to all the time we talked about logical implementation of quantum computer. Now we do talk about the physical one. So how do we design the actual working quantum computer? So there is a criteria called Devon sensor criteria. So which says that if you want to design a very stable quantum system, okay, your qubit should have following principles. One is the initialization to pure state. It has to have a longer decoherence time. I explained what is the decoherence time. It is a time within which you can sample, within which the quantum state is stable or observable. Okay, so you need to have a bigger decoherence time, and you need to have a universal set of gates. As I explained, the quantum gates now. All these things has to be implementable in the real system, and the readout has to measure the quantum state. It's all microwave. Okay, microwave or NMR. So that has to be very stable, and the interconnection of a stationary and flying bit, okay, that has to happen smoothly, right, and faithfully transmitted. Okay, the flying bit between specified location. All this is about the transmission. Okay, so Devon's criteria say that this has to be met in order for you to construct a good quantum computer. So this is a paper you can refer. This is where there's a very foundation of all the implementation of all the quantum computers. Now, physical implementation. How can we implement quantum computer? There are different physical implementations. One is superconducting, which is most of the supercomputer today, like what Google has done, what Tesla has done, are based on superconductors. Okay, but look into the decoherence time, right? Coherence time. It's like very very less, like 0.004 zeros divided by 5. That's very long the qubit can be stable, and you can't assume these qubits, right? So, and then success, logic success rate is 99.4, and you can go up till 9 entangled superqubits. Currently, we have only implemented until 9 entangled superqubits. And second thing is based on trapped ions. It's all laser and photon, where we trap the ion, and that will become our qubit, spin qubit, and then we control the ion using laser, right? And then decoherence time is thousands of seconds. Coherence time is thousands of seconds, so that you can comfortably observe the quantum thing, and you can go until 14. Today, I think it's like IonQ is a company which has implemented this, and they have 14 entangled qubits. Okay, very highly, very stable, and highest achieved gate fidelity. Okay, operation is very slow, and we require many lasers here. And silicon quantum qubits. QPI is doing silicon quantum qubits, and we get a coherence time as 0. It's like 30 milliseconds, right? So that is good enough for us. And we can use something called as single electron transistor, which can be fabricated, and we can build at scale, and it is controlled by microwaves, okay, of electron, and build on existing semiconductor technology, because semiconductor technology is 100-year old, and we can build it on them. And entanglement is problem, and the temperature is a problem. We have to keep it at very low temperature. And other two things are diamond vacancies, okay, so where we can get many entangled qubits, we can go until 6. And coherence time is very long, 10 seconds, okay. And other thing is topological qubits, where it is like it will greatly reduce error, and existence of this is yet to be confirmed. So we are going for a natural material which has topological qubits, and Microsoft is a big proponent of this, but still we don't know whether they exist or not. So if you want to build a good quantum computer, we need to actually implement quantum error correction. Okay, so the quantum error correction errors are resulted by bit flip, phase flip, gate errors, decoherence time, redout error. So there are 5 types of error, and we should be able to actually correct this all 5 types of errors, right? So we cannot achieve a bigger quantum computer unless we master the error correction. Unless we create something, there is a measurement called quantum volume. Unless we create a good quantum volume, you cannot build a good quantum computer. That's the reason now everybody, including QPI, is trying to build a very resilient quantum computer. Okay, that's our biggest motto. Current quantum hardware is also called noisy intermediate scale quantum computer, because it's very noisy. Your measurements will never be accurate. Okay, so how do we mitigate this? Using error mitigation, reduce the noise in system by hardware specific insight. Still, error correction is not applicable, but we can design it to be lower error, right? So, what are the coding techniques we have in the quantum error correction? We have, repetition code, stabilizer code, and then CSS. That's a very good coding. And there are some codes called quantum black codes, okay, and then quantum convolution code, and there are something called a surface codes also, okay, which is coming to right now. And the way we actually generally do the quantum error correction is we have a system, and we have encoding and clear, and then environment, okay, and then we collect the syndrome, even like classical thing also we collect the syndrome, and then we have an error correction and decoding. Okay, so these are the different steps. It's very similar to classical, but the kind of code we use is different. Okay, you can't use a classical convolution code here, or a classical reed solomon code here, so it has to be in the quantum world. So, what are the implication once we implement on this? What are the implication of this on our real life? So, one of the things you can know is RSA 204 write encryption. How long it takes to break using a classical compute? It takes around 317 billion years to break in the classical compute, and in the quantum compute it takes 10 seconds. Okay, so that is because but that is because of Shor's algorithm. Okay, it can do the prime factorization very very fast. Okay, and all this integer factorization like for AES and RSA and then Def-Hellman crypto system, elliptic curve crypto system, these are all can be broken very easily using quantum computer. I mean, current implementation, all your security can be broken very easily using Schwartz algorithm. Then second algorithm is called Grover's algorithm. Okay, and then what we have is in the Grover's algorithm, how do we estimate solving this collision problem? Okay, so Grover's algorithm can be used for search. Okay, can be used for cryptography and can be used for optimization of NPR problem. Okay, so this is a typical Grover's algorithm which can be very easily implemented using quantum computer. So different kinds of quantum algorithm today is like quest for speed up. How do we speed up the computation using quantum algorithm? We have amplitude amplification, okay, unordered search, graphs, and then data collision problem, matrix problem verification, and phase estimation. Okay, second is a phase estimation, and third is Hamiltonian simulation, and then quantum walk. Okay, so these are the different kind of speed up we can obtain using quantum computer. And how do we do the quantum error correction? So this is how it is represented. Like, for example, if you have a noisy intermediate state quantum devices, okay, so what is very important here is this is a classical word. This is like a NISC verdant plane, okay, and then magic fort for error correction, okay, and then fort of alternate. This is where we want to obtain. If you want to be here in this fort, then you need to cross all these things and make sure it doesn't interact with the classical word. Noise from classical word doesn't go to this fort. Okay, that's how you can implement a quantum device. And the NISC device we have is universal quantum gates or even annular is a NISC. Okay, and the type of noise you obtain in the NISC device is logical gate errors, decoherence time, and thermalization, and can prepare quantum states with low circuit depth. It's not like many qubits you can implement. Maximum is 30 to 40 qubits. That's what we are today in the world. Okay, and then near-term application is quantum optimization, quantum simulation, and machine learning. So we cannot go everything quantum. So how about going into classical, hybrid classical quantum architecture, where we combine classical computer as well as a quantum computer? So basically, quantum computer cannot be replaced with the classical computer because it cannot do what classical computer does. So when we combine or offload whatever quantum computer does easily, that will result in a better computation system. Okay. So today, all the computer, even QPI is working on a classical, hybrid classic quantum classical architecture. It's not quantum architecture alone. We have classical optimizer chip and then quantum optimizer, quantum processor. We combine them to obtain the result. So other thing what we have to do before really implementing a quantum system is there are quantum approximation algorithms. Okay, there is a QAA and there is a QAA, and all this algorithm will give us quantum approximation, and we can implement it as a quantum analog, or we can implement as a quantum on a quantum simulator as well. It will approximate your quantum calculation and it will speed up the calculations. So QAOA is a typical system what people use to actually obtain the quantum equivalent of the calculation. The way it is done is we have a CPU which is a classical computer and you have a QPU which is a quantum computer, and the interaction between those they can have some kind of this max cut problem that can be solved using QAOA. Okay, that's one of the quantum optimization algorithm, quantum approximation algorithm we can use to obtain the better speed up. Okay. And VQE is another thing which can be used in molecular systems. Suppose if you want to do MD simulation, molecular dynamic simulation, you have to actually obtain this VQE, and then it will actually speed up your calculation. And again, this is a interaction between a quantum processing unit and a classical processing unit. Okay, and most of the things like energy consumption and all those things can be done using the classical processing unit, and parameter updation and measurements and all those things can be done in quantum processing unit. Okay, so another application of quantum computer is key distribution, quantum key distribution, and you should have known this BB84 protocol, which is very famous, and quantum key distribution is current we are using in our quantum cloud. And what it requires is it's not classical here. Okay, the key distribution itself can undergo in a optical switch. It will not be in a typical electrical channel where usual AES or RSA key distribution happen. It has to happen on a quantum this optical switch. Okay, so this is one of the application which is happening today. We can implement this today. Okay, so any questions here before we go to quantum application? Okay, so you can do the if I wish I think if it was longer I could have given you a lot of assignments and I could have given it to work on our platform and obtain all these things. Created for our Quantum Explorer, very lightweight tool. We can do a lot of application. We superposition the ring of bells. Okay, this is a polyhedron representation of qubit. We can create a ring of bell here. Okay, and yeah, this is simple things practically you can do in the quantum computer today. Okay, make the match. Okay, yeah. So these are the thing exercises I had. If this was a live session and it was longer, but I'll just skip this and then I'll go to the quantum application. So accelerate quantum machine learning QML. I think Ashwant will take a bigger lesson on that after this session. Okay, quantum machine learning, that's one of the application. Okay, and then you have classical machine learning. How do we map this to a quantum tool like BLAS? BLAS is one of the matrix operation and it's a matrix library, and we have QBLAS for that. And then it can speed up your a lot of this classical machine learning. And then search. Instead of a classical search, you can have a Grover search, which will actually is much faster than classical search. And then the sampling, you have typical sampling on the model, and you have a quantum sampling here, and you have a combinatorial optimization, and then you have ground state optimization here. Okay, so these are the different things we can map 1:1 between classical and quantum. So why AI for quantum for AI? Because classical neural network can be easily represented by quantum quantum machine learning because of the gate structure. Okay, typically all the neurons can be directly mapped to your gate formation, and then you can obtain the hybrid neural network modeling integer classical quantum and uh, integrating quantum and classical nodes is very easy. Okay, so that is where the machine learning will be accelerated faster using this kind of structure, because we believe that in future the intelligence modeling will not be only neuron, it will be combination of bits, neuron and qubits. Okay, so the classical quantum machine learning is all about combining these three data structures. So again, training the machine learning models on the quantum device is very easy because of combination of quantum and classical devices. Okay, so you see that typically the weight updates and the way you calculate your you know the weights or the stochastic gradient descent, right? So that will be much easier when we combine classical and quantum device, because some of the operations in this optimization, unconstrained optimization, will be much easier on a quantum device than the classical one. Classical one may take more time and quantum will take less time. And hybrid of this, some of the things that can be done on classical cannot be done on quantum, and vice versa. So when we combine this, we get a better training speed up. Okay, you train a model, it will be faster. And coming to quantum optimization, this is the sweetest part where we are actually today using our logistic optimization, deconvolution of traffic will be based on this. Okay, it is based on two things: quantum tunneling and adiabatic evolution. Okay, so we this is typically is used in quantum annealers. Like for example, if you consider any D-Wave system, D-Wave is a company which came up with it is working on quantum computer maybe for last 20 years or something like that, and they work on quantum annealer. Most of their chips are used in quantum optimization. Okay, so these are the two principles what we use in quantum optimization, and with this we can really reach to absolute minima. Okay, so unlike classical, if you have a large subspace, reaching to absolute minima is almost impossible. Okay, so using these two principles and converting your problem to QO. QO stand for quadratic unconstrained binary optimization. Okay, so you need to convert any problem to cubo, and this will be converted into icing. Icing is a structure representation using spin. See, this one is a spin. Okay, and this one is your noise. Okay, so basically, when you represent all these things connected qubits via spin, right? And this this quantum tunneling will be very easier, and even like solving this in digitally is also very easier. Okay, you don't require a quantum compute to solve QO. You can use quantum inspired, but it will not be as quantum computer, but still you can solve some of the bigger problem today. So, what are the quantum inspired algorithm? As I suggested, we will not wait for the perfection where there is a quantum computer and you can solve a lot of things. There is a quantum inspired algorithms. Okay, so one of the algorithm is annealing, simulated annealing, and replica exchange, stochastic neurons. Okay, and then you have QIA for recommendation system, and you have for PCA also you have, and then there is QI for solving low ranked linear system, not high rank, low rank one. And there is a quantum cubo based problem, which is icing problem, icing computation. Okay. And today we can do this using quantum inspired or using NISC. Okay. So as a company, we are working on this one, and this is coming up very soon. A near-term application for quantum compute is quantum machine learning, optimization, simulation, and material and pharmaceutical and cybersecurity. Okay, so these are the application you're going to see in next 5 years. And then what we can do in quantum computation, we can do quantum optimization, quantum machine learning, quantum simulation, and some of the other optimization problem like smart grid optimization, wireless network optimization, job scheduling. On the chemical side, pharma and petroleum industries, we can do supply chain optimization, optimizing reaction networks, and then disease diagnostic is a very important thing that quantum computer can really play a big role. And then for oil and gas field, gas companies, anomaly detection is very important. Where we are seeing that more and more classical machine learning is not working, and we may require quantum one. Okay, and other thing which is more important for humanity is drug similarity search. Say, for example, if there is a drug XYZ and we want to search similar drugs so that we can just obtain the better performance. Okay, quantum computer can be very useful. And inverse drug design. Okay, so and then the protein folding, genomics, drug discovery. So these are all extremely important for humankind, and quantum computer can play a big role here. And other thing is on finance. Finance, there are fraud detection, credit scoring, option pricing, and then crash forecasting. Okay, and then your portfolio optimization, security. Okay, so these are all where quantum computer can help in finance. So coming to hardware, what kind of hardware we can build? So currently, as a company, we are working on CMOS-based quantum qubits. Okay, so we are building a chip which works at 4K, 4 Kelvin. Okay, so typically a quantum qubit can be done at 20 millikelvin, and there is a control circuit. It's all cryogenic. Okay, cryogenic is it is cooler than interstellar space. Okay, that's where the quantum computer can work, right? And so we are working on this silicon technology, and this is how it is built. Okay, we can build a scalable quantum qubit. So other thing what is important in quantum compute, as I told, like we have a classical chip and then the quantum processor, and there is a control circuit. So all three put together will form our quantum hardware, and we have a big software stack here. Your basic quantum application will be running on the PaaS, platform as a service, and then quantum application, quantum algorithm, high level programming, and underneath that you have two compilers. Usually in any protocol stack, any software stack, you have only one compiler. You have two compilers here. Okay, classical compiler and a quantum compiler, and they have to interact with each other. Look into this, like, and after you have a compilation of a quantum software, it has to be converted into control pulses. Okay, microwave pulses. So this is a circuit, the intermediate circuit, where the microwave pulses are generated, and then it has to go to quantum dots, and then it has to actually, the classical one will end here. Okay, with the classical optimizer chip. And this is a hybrid system I'm talking about. There's a classical chip, there's a control chip, and there's a quantum chip. This is a a practical way to implement the quantum system. Okay, so that's what I have. And any questions? I'll be open for the question. Hello. Hello.
Sir,
Yeah. So I'm done with the presentation. Any questions for me?
ask the participant.
Yeah.
Yes. So, dear participant, if you have any, sir is answer your question. So, if any questions, any queries, please raise. If you have any queries, please. I think not, sir.
Okay. You can ask me offline. I'll be able to answer.
Okay.
And you have a nice day. Thanks a lot. Bye.
If you have any parent have any questions, I will use it.
Sure. Thank you.
Thank you, sir, for your
Sure.
presentation. It is the how to do the practically very nice presentations. Thank you, sir.
Thanks. Bye.
Thank you. So, who is logged in through the voice? Please put your mind. Username voice. Please, please check. Okay, the next session will start at. So, please stay in meet on the next start at 30. Okay. చేసినట్లేను అందరికీ అని మళ్ళీ పెట్టినట్టు పెడతాను సార్. అందరం అదే పెట్టుకుందాం సార్. అది ఒకటి మాడిఫై చేస్తానండి సార్. ఆడ మాడిఫై చేస్తే అందరికీ ఇది అవుతుంది కదా. నేను చెప్పాను సార్, ప్లీజ్ ఆల్ ఇఫ్ మై బ్యాచ్ స్టూడెంట్స్ ఆల్రెడీ ఇగ్నోర్డ్ అని చెప్పినాను, అందరికి పెట్టమని చెప్పాను. నాకే వస్తుంది సార్, నేను చెక్ చేశాను. ఓకే సార్, బాయ్ సార్. భవ్య, భవ్య, ఏం లేదు. సార్ ఉండిన్నారు ఇక్కడే, చెప్పాను. ఏమవుతులే. ఓకే. థ్యాంక్ యూ. ఏంటి సోఫానా చెప్పానా? ₹350 షాపింగ్ షిప్పింగ్ కి పడుతుంది. ఈడికే పెట్టానా? ఆ డ్రెస్ కూడా చూడే, నువ్వేమైనా చూస్తానంటే నీకు దీంట్లో ఇస్తాను. అది ఒక మెటీరియల్ కావాలన్నావు కదా, చూడు. నేను అక్కని అడుగుతా, అక్కకి ఏమైనా కావాలంటే. నువ్వు దీంట్లో ఏమైనా సెలెక్ట్ చేయి. ఇప్పుడు వచ్చినాయి శారీస్ అన్ని మెటల్ శారీస్. నేను మా అక్కని అంటాను, అక్క ఏమైనా కావాలనుకుంటున్నా. సార్ మంచి ఒక చూస్తావా ఫంక్షన్ కన్నా ఏం లేవు నాకు ఫంక్షన్ నేను కూడా వాడికి పెట్టాను నేనైతే పెళ్లిలో మీరు చాలా మా అక్కకు ఇంకా మా అక్కనే ఇప్పుడు చేసుకుంటుంది. అదేంటి జీపే లేదు మా అక్క దానికి, అదొక్క దాని వల్ల నన్ను అక్కడికి వెళ్ళి బ్యాంకుకి వెళ్ళి అది ఇది చేసుకొని ఇంకోటి తీసుకో. మా అక్కది కూడా అది ఉంది, అది పిన్ తెలియదంట. కొన్నిటికి వేరే కలర్స్ ఉంటాయి కదా. 23, 24 ఎవరు లేరు కదా మనకి ల్యాబులకి ఏం ఇబ్బంది ఉండదు కదా. అయ్యో Sir, good morning, sir.
Hi, good morning.
Good morning, sir. Yes.
Yeah.
Now sir, dear participants, now the session will handled by the Ashwant Krishnan Garu. Before he's going to start, I want to introduce him to you. Sir presently working as the researcher at QPI AI. Sir has 9 months of experience at QPI AI. Sir involved in developing hybrid quantum classical algorithms for near-team quantum computers. Sir completed his master's at National Institute of Technology, Karnataka. Sir completed his undergraduate at Birla Institute of Technology. Sir, thank you, sir. Sir, please hand over the session, sir.
Okay. First of all, thanks a lot for having me here. So I will present my screen and start my talk.
Okay, sir.
Is my screen visible?
Yes, sir. It is visible, sir.
Okay. Okay, so the title of my talk is Machine Learning with Near-Term Quantum Computers. So, so at QPI, what we are exploring is with the quantum computers that we'll have in the next 5 to 10 years. What can we do with them? And how can we enhance machine learning, especially accelerate the training time as well as get better machine learning models with them. So, machine learning as a field has seen enormous progress in the last 10 to 15 years. Like it has been used in potentially all fields in science and technology. Uh, and so there is a lot of commercial value in actually cracking machine learning and even improving it subtly. Right now, the state of the art of training machine learning models is using special purpose GPUs, special purpose FPGAs, and ASICs. So at QPAI, what we are also exploring is how we can use quantum devices to do this. So in this slide, I have two sections. One is quantum devices and one is QPUs. On by QPUs, what I mean is quantum processing units. So this is what the forefathers of quantum computing envisioned as a quantum computer with millions of qubits, fully error corrected qubits. But this is a long way off from where we are. So what we are mostly interested is how we can use quantum devices with thousands of qubits, but noisy qubits with a lot of errors, and still somehow use it to gain an advantage. Here in this table, we see that there are four different ways of machine learning. So here in the y-axis, this is the data. So if your data is classical, it's denoted as C, and if it's quantum, it's denoted as Q. So what we are exploring is how we can use a quantum processing unit to process classical data as well as quantum data. So these are the two main avenues that we are looking into. Okay, so what is machine learning in a nutshell? So in machine learning, we have some data as X, and it has some outputs, and it has some relationship between them that we want to infer from the data. So this is what we want to figure out. This is the main aim of machine learning. So here in the x-axis we have the data, and on the y-axis we have the output, and we need to fit a model to this data such that it performs well on data it has not seen. As you know, data is the new oil, and finding out new ways to process and infer from data is actually a really important thing that one has to solve. And the next main building block of machine learning is a model. So here we have a linear model in the left side. So a model is actually a relationship between the input and output that is parameterized by some value. So here in this line, we can parameterize by a slope of this line as well as the intercept of this line. And different values of these parameters will give different models. And this whole model class can be called as a linear model. Similarly, this is a different kind of model. So the goal of machine learning is to fit a model to a data, especially supervised learning. Fit a particular model to a data that we have. The next building block of machine learning is a loss function. Given a model and given some data, how well does that model perform? So this is a qualitative way to compare the output of our model and compare the actual data that is present. So here we have a model like this straight line that we are using to fit our data. And since this red dot is actually very far from this line, there is a high loss function. Similarly, the goal of machine learning is to actually find a model that minimizes this loss function. Okay. Now coming to the quantum picture. So as in the previous talk, we have seen what are qubits. So I will just briefly go through the main concepts. So a qubit, as like a bit in classical computing, the qubit is the smallest unit of information in quantum computers. So on the left side, suppose we have n qubits. This can be realized in a variety of ways, but at QPI, what we are interested is CMOS based silicon quantum qubits, which are spin qubits. And given n such qubits, the information that's stored in this qubit is actually represented mathematically by a 2 to the n dimensional vector, where each entry of this vector is a complex number, and those denotes the probability that when we make a measurement on these qubits, what would be the answer. So you see that on actually representing n qubits, we actually need 2 to the power n numbers. So this is actually an exponential overhead. So suppose we want to process qubits on a classical computer, we need to do linear algebra on 2 to the power n dimensional vectors. So this is actually really hard to do. So this is why one cannot efficiently simulate a quantum system. For instance, if we have like a molecule which is a quantum system, simulating those molecules on a classical system is really hard because of this quantumness. So this is one of the main reasons that people were interested in quantum computing. So with n qubits, one can simulate quantum systems very easily. And so since these entries in this vector are probabilities, all of them needs to add up to 1. So in this high dimensional vector can be visualized in a nice way as this block sphere. So this is because the points on all of these points on the sphere will denote a particular state of the qubit. This is because this is a sphere because the probabilities need always to add up to 1. So the basic difference between a bit and a qubit is a bit is a discrete value. Bit can only take up discrete values, 1 or a 0. But a qubit can take a set of infinite and continuous values. So how I like to think about it, the bit is a switch and a qubit is a knob. Okay. So how to build qubits? So this is a nice quote that I like from Asher Paris, that it's nice to talk about qubits as vectors and in some abstract Hilbert space, but actually a qubit is actually a physical object that is present in a laboratory. So there are different approaches to realize qubits, and the final details of this implementation would be covered in later talks. Okay, so now that we know qubits, what can we do with them? So we have a set of n qubits, then we can perform some operations on them, which I am denoting symbolically as a circuit. And mathematically, how we would represent is the state of a qubit is denoted as a vector, and an operation on that qubit is denoted as a matrix that acts on that vector. This cannot be any old matrix. This has a special structure. This is called a unitary matrix. This is because not all vectors can denote a quantum state. Only quantum states that are normalized and can be denoted as a quantum vector that is normalized can be denoted as a quantum state. And once this matrix acts on this vector, this would some ways rotate that vector, which can be visualized in the block sphere as a rotation, like this. So any operation that we can do on a qubit is actually a unitary operation, and all of them can be visualized as a rotation. Now so this is the point of computation. We initialize a qubit in some state, then we do some operation on that state, and then finally we make a measurement of that state. Once we make a measurement, we get a sample from a particular probability distribution, and we have to repeat this measurement a couple hundred times, thousands of times. The more the better. And then we have to make an average of these measurements and to get an actual estimate of our computation. So mathematically, this is denoted as an expectation value. That is, we have our quantum state, we do an operation on them, then we do a measurement, and then we do a and sign this measure between these two matrices. So finally, we are done with this multiplication. What we will find is we will find a number. That number is an estimate of the computation that we have done on our circuit. Yes. So any questions at this point? Okay. So going ahead. So now we have seen the basics of quantum computing. So how can we use quantum computing for machine learning? So some 10 or 20 years ago, like in the traditional ways of looking into machine learning using quantum computing is by using algorithms like HHL algorithm or quantum PCA algorithm. All of them relies on a particular algorithm called HHL algorithm that can speed up a matrix multiplication. So as you know, machine learning has a lot of subroutines that uses basic linear algebra. So if we can speed up them exponentially, then we can speed up machine learning exponentially. But the main problem with this approach is all of these algorithms require a fully error-corrected quantum computer, which we currently do not possess. So the new way of approaching machine learning with computers is something called variational algorithms. So the idea behind these algorithms is that we can work with these algorithms even when we don't have a fully error-corrected quantum computer. It can tolerate somewhat low amount of errors, and it is very robust. So since we are at this noisy intermediate scale quantum era, so here we are exploring these variation algorithms, and once we have a powerful quantum computer with full error correction, then we can think about the other approaches. Okay. So as any circuit that we can perform on a qubit can be broken down into a couple of universal gates that we can perform, and we can realize them. If we can realize these universal gates, we can realize any old circuit. So this is similar in spirit to how in classical computing we have these NAND gates, NOR gates, and stuff. With those gates, we can do any classical operation. Okay. Now coming on how we can use this quantum computer to get a newer class of models that we can use for quantum machine learning. So the basic idea of a model is that we have an input and we have an output. And model can be parameterized and can represent a particular type of relationship between the input and output. A quantum computer can actually provide a new type of models that we can use for machine learning. So the first step would entail on on mapping the our input data onto a quantum state.
Excuse me, sir.
And, yes, please go ahead.
Sir, I'm funny. Yeah, there's this basic question, sir. Generally, if I use a classical computer, I will be using classical data. It might be categorical data, discrete data, or continuous data. It will be in the form of zeros and ones. If after pre-processing this data.
Yes.
But in quantum computing, the main task is I'm collecting qubits. I mean, the information in the form of qubits instead of bits.
Yes.
But in normal in our day-to-day lives, there will be only classical data. So for a particular use case, there won't be any kind of generally you are going to solve a client's problem statement, sir. Example, risk management for a finance sector. So there will be classical data. Client won't collect quantum information. There will be information in the form of classical data, in the form of bits. I mean, quotations, all these things. So how can I apply quantum? How to apply quantum computing over there? So there won't be any classical data, right? I mean, there won't be any quantum data. There will be only classical data. So how can I apply these? How can I solve day-to-day lives? I mean, if I go any company or any IT service, data. Client will be giving me only unstructured data in the form of classical data. So how can I apply quantum on these?
This is actually a very good question. So this is still an open question of how we can encode classical data on a quantum computer the best way. So the approach that one use is encode. We use some kind of encoding to encode the classical data we have onto a quantum state. I will more detail in the late coming slides. So the idea is somehow encode the classical data onto a quantum state and then do a processing on that quantum state and then do a measurement and get some outcomes.
Sir, in that scenario, sorry to interrupt you, sir. In that scenario, if I use encoding techniques, for example, any encoding technique in quantum or machine learning, so for converting classical data into quantum, I mean, it is taking time, and later on, I mean, classical data there might be consider the classical data is unstructured data, so. You are converting that unstructured data to, by using encoding, you are converting that unstructured data to quantum data. I mean, qubits. Later on, again, it is unstructured, right? We should handle the data again, missing values, layers, and then if there are any null values. So again, I should pre-process all these things. So in that scenario, my entire day on data pre-processing is more.
Yes, that is true. But what if this quantum has some and it has better expressibility and it can find patterns on your data? So this is the hope of quantum machine learning at this point. Once we encode our classical information onto a quantum state, then maybe a quantum model can perform better on this part. So it's not the main driving force at this point in the near-term quantum computing for machine learning. The hope is that these quantum models are more expressible and will generalize data better than quantum model, purely classical models. And the state of the art is how can we combine both quantum and classical models such that we can use the best part from each bag. So that is the idea. So your particular question on encoding is actually a really good question, and there is not a definite answer for how the best way to encode data. There are multitude of ways we can encode data, and it is mostly a process of trial and error at this point.
Yes, sir. Thank you, sir.
Okay, thank you for the question. Okay, so yes, so the current approach to machine learning in quantum computers is this paradigm of variational quantum circuits. So here we start with some fixed state, and we have a state preparation circuit that prepares a state depending on the input data. So this is the encoding part that was discussed. And once we have our data in the form of a quantum state, then we can perform some unitary transformation on this state that is parameterized by another set of parameters theta. And then at the end we do a measurement and we get some outputs from this circuit, and based on this output then we can do some classical post processing and we can get a final output y. And this is the quantum model where we input classical data x and we get an output y, and which depends on this parameters theta. On a mathematical description, this is a matrix that does the state preparation. This is the variational part, and this is the measurement part. Once we are done, we will get a real number, and we would interpret that number as an output of this quantum model, and we would train this parameter theta just like we train a neural network, the weights of a neural network. Yes. So the particular part of data encoding is that we have classical data which are vectors, that are real vectors, and then in the encoding part we encode these real vectors onto a Hilbert space of quantum systems in such a way that we can use these quantum states to perform machine learning. So this is similar in spirit to the kernel methods and related methods in machine learning, where one map the input space to a higher dimensional space through a kernel function. So this is similar in spirit to that method. Then how we do this encoding and also how we do this processing, one usually has a specific structure to all of these circuits. These we call as ansatz. So here we have a bunch of fixed Hadamard gates, some fixed structure of gates, and some of these gates will depend on some parameters. Like in this first case, this circuit depends on beta 1, beta 2, and beta 3. So these would be real numbers, and depending on these numbers, this circuit would be different. So these ansatz we can use to either embed the data if these numbers are data points. Let's say this is this denotes the let's say height of a person, weight of a person, and age of a person. Then we can do an encoding of that data onto a quantum circuit in this fashion. On the other case, these parameters can also represent the weights of this quantum neural network. Like if these parameters, if we let them be trainable, then these would be the weights of this quantum neural network. And so this I think we can now see the similarity between a quantum circuit and a neural network. So in a neural network, we have some inputs. We do some matrix multiplication on those inputs. We do some nonlinear activation functions, and we chain a bunch of them together to get an output. So in this case of a quantum circuit, there also we have a set of inputs as vectors. Then we do some matrix chained set of matrix multiplications on them. So in this slide, I am showing this graphically. So formally, we have a data encoding map. Then we have a unitary transformation part. We have a measurement and we have a post processing. In the circuit model, we can visualize them in this way. In graphically, this is similar to a neural network where we have a data encoding, then a bunch of deep layers, then nonlinear activations and post processing. So this is the main motivation for using quantum circuits as neural networks. Okay, so now we have a neural network, then how will we train them? So the most promising approach to training neural networks currently is a hybrid quantum classical scheme, where we prepare a circuit based on our input and the trainable parameters theta. We do some measurements, we get some information from this, we pass that information onto a classical computer, and we we do classical gradient descent on the classical computer and optimize our parameter values to obtain the minimum of our cost function. And this is an iterative loop that happens between the quantum and classical device. And finally, at some point, we will train the model, and then we can use this quantum model for whatever machine learning task like classification, regression, generative modeling, whatever. So the main philosophy behind these algorithms is that we have a separation of tasks where the quantum device prepares a state, and it depending on some instructions from the classical device, and it would hand back the information, and then based on that, the classical device will make an iterative updates on the quantum device. Yes, so this is the main idea of hybrid computation. But the main challenge, one of the main challenge is that whatever the losses that we'll get from this quantum device is actually trainable. So in machine learning, we have a loss function, and we start with some random parameter values, and then we try to minimize this loss function. So in classical machine learning, it turns out that in most cases, this loss landscape is actually really nice, and it can be trained. Like once we start from a point, then just by doing normal gradient descent, one can reach a sufficiently good local minima. But in the quantum case, there is a problem plateau. So loss function, we see that we start at this yellow point. Then this yellow point is is a really flat region, and there is no gradient information that where should we to actually minimize the loss function. So this is trainable loss function. So it turns out most of the quantum neural networks that if we naively take a random circuit structure and then try to optimize it, the loss function will typically look like this. So it's bad news. But the reasons for solving these problems that if the circuit of our circuit is low and the cost function is local, and if the error rates are low, then we can successfully train them. So this is still a question on how we can make networks more trainable. So coming on to the paradigm of hybrid quantum classical circuits, here what we have is these bunch of nodes, and cost that depends on these bunch of nodes. So these pink regions, these are classical nodes. They might be classical neural or some classical processing layer like Fourier transforms or whatever. Then there is this bunch of blue nodes. These are quantum nodes. They can be quantum neural networks or some particular differentiable quantum algorithm. We chain a bunch of them together, and then all of them depend on some parameters theta, and we do optimization on these parameters to obtain good result. So this is the hybrid quantum classical neural network. So just like how we train a normal neural network on a TensorFlow or a PyTorch, just by using the backdrop algorithm, one can train these high classical networks. Yeah, so in a particular quantum node, we can parameterize the node in this way using some of the sets that I had shown in the previous slide. Yes. So, what are the opportunities of quantum machine learning? So, one of the main point of quantum machine learning is that now with near-term quantum computers, we can do machine learning with quantum data. So, suppose we have some quantum data, for instance, some data from a quantum network, or maybe data on some protein structures, or all of these data from quantum sources. So, to actually get a good representation of them, we actually need exponential number of resources. Uh, but with a quantum device, we can store them in a polynomial number of resources. And this is very efficient, and one can do machine learning on this data, which is not currently possible efficiently. And this provides us a newer class of expressible models that we can use for a variety of tasks. So the open questions in this field is for which kind of data sets can these approaches give the best advantage, and which optimization scheme to use to optimize these because of this barren plateau problem, and also the which circuit structure works best for encoding as well as the model. Okay, so thank you all for listening, and if you have any questions, please go ahead.
Yes. Anybody have doubts? Please raise. Please raise and ask. So, dear participants, if you have any doubts, please. Yes. If you have any doubts, please ask.
Also, if there are some doubts pops up in this field for anyone, please contact me offline also. Like I would be happy to.
Okay, sir. If any participant will ask, I will post you through mail. So I will send your mail to them.
Sure.
Thank you.
Thank you so much for listening, giving me this stuff.
Thank you, sir, for the wonderful session.
Thanks.
Thank you, sir.
Hello?
Hello, sir.
Sorry, I dropped.
Oh, okay, sir. Sir, please continue the session, sir.
Okay. So, if any one of you have any questions regarding this or some clarifications that some points that I need to stress on more, I would be more than happy to actually go through it in detail because I feel that I rushed through some of these things. So, if somewhere we need any clarifications, please go ahead and ask. Mm. Okay. So,
Sir,
yes, please.
you only explain what are the research areas in this, how it will be useful for the research areas.
Yes. Yes, as I was discussing, so this is actually this quantum machine learning is actually a really old field, but recently there has been a shift in perspective in this in the community that the traditional algorithms all they cared about is speed ups, like how fast can you make the training or how fast can you make the inference? Is there an exponential savings in time? uh, all of these things. But this point of view has been changing. These days, people are more worried about how can we make use of whatever things that we have currently and make something useful out of it. Can we make the models, machine learning models, more expressible, or can we use this for newer types of data sets that is currently not possible with traditional machine learning? So this shift in perspective is actually really nice, and this actually opens up the possibility of commercial advantage in this space. This makes it even faster. Like with the traditional approaches, the horizon of commercial advantage was always 10 or 20 years down the line. Once we have millions of qubits, once we have error correction. But with this paradigm of variational quantum circuits and quantum machine learning, things seems like within 5 years we can have a commercial advantage. So there are a lot of problems also with these approaches, especially the one that I pointed out was this problem of barren plateaus. That these are highly expressible and really nice, but uh, 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 actually training these models becomes a little bit tricky most of the time because of this problem. Then so there the currently the improvements is in two directions. One is in realizing better and better hardware with better connectivity between qubits, better lower error rates, and better set of universal gates. And on the hardware front, all of these are happening at an exponential pace. Like the number of qubits is doubling each year, kind of like a Moore's law for quantum computers. And on the software side, the main challenge is to actually come up with hardware efficient algorithms with a lower number of qubits and lower high error rates, even then these algorithms should be able to perform well. So error robust algorithms and hardware efficient algorithms, and then the better compiling strategies for mapping a particular algorithm onto a hardware. This is another area of research. So given a quantum circuit, how can we map onto the gate sets and all the hardware specifications of a particular quantum computer that we have? So this is a compiling problem. This has a huge impact on the trainability and as well as the usefulness of these algorithms, because on theoretically all of these algorithms sounds nice, but actually on actually implementing them on a real quantum computer is really a challenge. Also, the next avenue is the theoretical foundations of these algorithms, like what is the how these models generalize, what are the structure of these models, what are the data sets that are best suited for these models, and how can we uh, improve the how can we improve the ansatz choice based on the symmetries of our data set. All of these are theoretical endeavors that are going on parallelly. So uh, uh, already companies like IBM, Xanadu, and also us, all of us are trying to come up with commercial applications for this algorithm as soon as possible. So one area that is most promising is I think is on the drug discovery pipeline, where and also these chemical simulations, biological simulations. All of these data are inherently quantum, and they have quantum correlations in them. So it is the hope, the community, the belief of the community is that on these data sets, quantum models can perform well and can perform patterns better than traditional machine learning, like deep learning. Yes. So these are some of the main points on research in this area.
Sir,
Yes. So another thing that is interesting is how one can use classical machine learning for for actually uh, implementing quantum computers. So it's the reverse problem. How we can enhance quantum computers with classical machine learning. So this is another area that we are exploring at QPAI. So the idea is that these quantum computers are very fragile and they have a lot of control parameters that one has to tune for these things to work properly. So till now, the most approaches are experimentalist, working hard for days to calibrate them by hand. So this can be easily recast to a learning problem, and one can use traditional machine learning algorithms like reinforcement learning or similar things on this avenue. And this is uh, uh, another approach of combining machine learning with quantum, but not for an advantage on the machine learning front, but using machine learning for an advantage on the quantum computing front.
Sir, real-time applications. Sir,
Yes. So that's all the content that I had in mind. So if there are more questions and discussions that we can have, that would be great. Otherwise, I think I'm up.
sir, how the this quantum computing, the qubits are used in blockchain, and so what are the various real-time applications? So
Of
where
blockchain in blockchain.
yes, how it is useful in a blockchain and AI.
Yes. Okay. So so as was discussed in the previous talks, so there is an algorithm called the Shor's algorithm. So what it can do is it can, given a really huge number, it can factorize that number onto its prime factors like really fast. So the current encryption schemes that people use, for instance, even in blockchain or let's say whatever communication protocols that are followed, RSA encryption, it is based on the fact that classical computers cannot factorize huge numbers efficiently. So the security aspect of these algorithms comes from this fact. So since Shor came up with this algorithm, one with a really powerful quantum computer can easily break these encryptions and can actually bypass all of these blockchain securities that are put in place in these systems. So the The application here is that it's not application, it's a necessity that one has to come up with new encryption schemes that are resilient to quantum computing. So there are two approaches here. One is post quantum cryptography, that is develop new cryptographic algorithms that does not rely on this fact of this problem of factorization, and even with Shor's algorithm we cannot break it. And the another approach is to actually come up with quantum algorithms for cryptography that rely on quantum computers. So the good thing about these algorithms is that these things are inherently safe. That these even with the most powerful quantum computer, or if post quantum computer, maybe a computer that relies on some unknown physics or whatever new technology that comes, the security is unconditional. Quantum cryptography based algorithms provides unconditional security. So one can use these algorithms in blockchain, and then one can call them quantum blockchain, and these provide better security aspects. But the good thing is that we still have a good amount of time to actually think about these things, because in order to implement a Shor's algorithm, one would need millions of qubits to actually break RSA encryption using Shor's algorithm. So that is, we have time till we can have that powerful quantum computers, but it will happen eventually at one point. So better start thinking about these things right now. On the AI front, as I was discussing, there are two aspects. One is increased training speed and inference speed, which is offered by algorithms of the type HHL algorithm, which also requires a really powerful quantum computer. Maybe 5 to 10 years down the line, maybe we'll have. The another aspect is better expressible models that are offered by this variational algorithm paradigm that I was discussing in my presentation. So this would mean better validation accuracy for your models for new types of data sets. So I hope I have answered your question.
Yes. If anybody have doubts. If anybody have doubts, please. So this is the 10 minutes to solve your problems. So whatever where you're going to getting the problems as a so dear participants, please use this time, utilize this time. If anyone have the questions or queries, so please. Okay, sir. Okay, sir.
Yes.
Okay, sir. Thank you, sir.
Yes, thank you. Thanks a lot again for having me here. It was really nice to talk about these things. Thanks.
Thank you, sir.
Thanks.
So today, the next session, the afternoon session will start at 2:30. So actually, we have the another class due to some personal reasons. So due to the accident to the sir's father, so he is going to be leave. So the afternoon session will start at 2:30 to 5:30, and the topic is soft skills for professional development. Soft skills for professional development. So the participants please joined into the class at 2:25 only. 2:25. So the session will start at 2:30. Okay, thank you. Thank you all.